Can you see my screen?
Not at this point in time, but you need to move it. Wait a minute.
Wait, let me
I'm
check.
going to move this over.
So, desktop 2.
So now I think we can see your screen, but not yet presenter mode. Yeah, now
Okay.
now you can see it.
Okay, great. So thanks everyone. Sorry for not being there. It would be great to meet everyone in person. But traveling has been crazy these days, and I'm a little bit sick, as you can hear from I got a cold. But it was great to hear all the talks today and get to know everybody online. So what we're gonna do at QCFD, actually, the previous talk by Felix is very much on aligned with what we'll be doing as well. Probably we'll split it in terms of platforms, and I guess we can share approaches. We'll do a little bit more as well on what I call the Hamiltonian or the hybrid analog digital approach. So these are extracts from the project, kind of a little bit refined as we have them at tasks there at different work packages. But basically, we work with experimental hardware groups in the Europe to optimize the code that comes out from the original QCFD papers of Dieter and everybody else. And really, there is a lot to do, as Felix was saying. When you have a first circuit that calls for certain gates and certain implementations, when you go on the real hardware and you look at the native interactions, you look at the native gates available there, even at the Hamiltonian level, there's a lot that can be improved. So we'll look at realistic noise models. We'll do pulse optimization, pulse shaping. This comes under what we call also quantum optical control. There are ways to combine that with machine learning to do it more automatically. And we'll also look at breaking some of the circuits to digital and also Hamiltonian evolution. It's possible actually to do some interesting things when you go one level down, closer to the hardware, and use your naturalizing or Bose-Hubbard if it's cold atoms, or long-range Ising models if it's ions, to implement some of those things. And as we say in the proposal, in the project, this should this platform optimized codes and circuits should interface with gate level, but also the analog, ideally the analog machines available, and with the standardized APIs, QSKIT, for example, or whatever other API people might be using. And I think Pascal or some of others guys might have their own APIs. And of course, we will, compare the results, benchmark against each other, benchmark against the numerics done by Dieter and his team on the tensor network approaches, and then check what is the optimal suitability of the hardware to realistically implement at least certain instances of what we'll be doing in this one. What we've done so far, in this case, again, can refer to the earlier talk by the morning, where we have started from the basic, looking at the nonlinear circuit equation, which was the first type of the first paper. And what we did, I'll go in a little bit more detail in a bit. We simulated the circuit using the cheat method, not the Ancilla qubit method, and it works very well, just so we can find our, finding our fit, implementing both the circuit and the quantum nonlinear unit. It works perfectly in simulators without noise. The results kind of look very, very nice and encouraging, as also in the paper. And now we're adding some noise models and trying to make a first effort to change those early circuits into something with, let's say, native gates. For example, instead of superconducting models, you have, it's easy to implement control phase instead of control not, or control Z gates. We want to see how that will affect. We are also progressing on the Ancilla, the full thing, using this control swap gates from the early days, as we discussed this morning. And we're looking for ions and Rydberg atom actual implementations. On this, I can jump a little bit before I go back to 3 and 4. We reached out to Alex and Planck QC. They have a nice setup. It's still not fully developed. One worry I have, because I guess this is a chance to talk about possible worries, is we had experience with the Rydberg machines built by Amazon. Basically, these were Michel Lukin's spin-out machines that were kind of bought or sold at Amazon. The problem in these Rydberg ones are the low measurement efficiencies of the detection, actually. And for certain cases, this might be an issue. Other than that, it's an interesting part that you can play with quite a bit of range of Ising models they can implement. A more promising one seems to be with the Alpine quantum technology. We mentioned it earlier. We had a few changes, and we plan actually to talk to them as we evolve the next few weeks. We just hired a few people actually as well. It took some time. And you know, the one array, Ioannis and there is Mohammed, which is also in the call, and Sophia will be joining soon. We'll be working some of this. It seems with the situation with Thomas is they don't have cloud access yet, but we might be able to send the kind of the notebooks in their API. I think they can also use QSKIP, and we could, after we do our optimization and we prepare the notebook and it's ready, we send it over and they run it, and in that sense, it's like a more traditional theory experimental collaboration rather than going through the cloud. On these 2 points, they definitely relate to what we discussed earlier on what is out there, how many more hardware can we add here. I believe Zulik is one for sure, and maybe Pascal, as it was mentioned. We need to see which one are the best in terms of fidelities and access and control and measurement and pulse shaping control in order to see how to optimally implement this. A few words on the team. They are in the call, some of them now. Mohammed is collaborating RF, visiting RF. Sophia will join us soon, and Ioannis already joined. These are part of a bigger team that works on different things, including some NISC implementations of different phenomena. And I will say a few words on what we do and where we are now in a bit more detail on the technical side. So we work on quite a bit on what we call analog or Hamiltonian quantum simulation, where you basically take off this digital part, this gate decomposition, and you replace it with an analog, with a Hamiltonian-based evolution. And then this is kind of closer to the original analog quantum simulator approach by Feynman, where you have one system that you cannot really measure or control very well, and you use another one in order to probe various phenomena you expect that will be there. This was known until now to do mostly condensed matter effects and different strong correlated physics from material science, but recently there have been some suggestions, including from ourselves, that you can actually do interesting things like machine learning, for example, generative modeling using these analog approaches. Oops, sorry, classical computer crash. Give me a second. PowerPoint just crashed. Some big picture maybe. Back. So
you're not going to present 47 slides, are you?
Say again?
Are you going to present 47 slides in total?
No. This actually is much fewer. I'm almost towards the end. So one this was another talk with the one you saw here. These are backups from different talks. What we saw recently in designing these optimal instances is this is a different problem. This is chemistry. It's very important to build your instances in an efficient way, such that the number of gates, the depth of the circuit does not, explode as you put more and more qubits to implement your algorithm. And we have a good feeling how to do that for chemistry problems. I mean, slightly different, but there are some common angles there. And we recently saw that, for example, you can do up to large molecules, in this case, H12 or H14, using these techniques where the gate depth, the maximum CNOTs per circuit, compared to the standard approaches that go as n to the 5, which makes it forbidding for any NISC implementation. You can actually go with a linear size with the number of the qubits, and that allows you to do much more with less fewer qubits, basically. So I will skip this analog part. I will mention one interesting approach that combines this training and machine learning using both analog and digital. And we saw that this is possible to do for implementing cost functions that come from machine learning. And those cost functions have a lot in common with the cost functions mentioned earlier this morning by Dieter. You can have local and you can have global ones. And some of these things can actually transfer over and optimize the circuits and reduce the depth. And as I am the one before last, I will really be fast and finish with some one kind of something we have to take into account when we go on the hardware is that things look very, very different. This is a chemistry calculation, but it's similar to all use cases. Using our improved techniques, in this case, we could actually, calculate chemical energies for certain molecules with linear depth according to our theories. However, when you go up to 69 CNOTs, which doesn't sound like very bad, but if you really go on the hardware, it's very hard to go beyond, in this case, it was 41 knots we could do for an H2 molecule. So what I'm trying to say here is that the qubit chips that are announced by the companies that they are put online, and the numbers they are assigned there for gate fidelities, and actually most of the time they don't announce gate fidelities. The 400 qubit by IBM has not really been specified at all what can it do, but the smaller chips, the smaller they are, the better they work. Anything more than 15 or 20 gets really noisy. The 27 one, for example, in this case, we are not going to be using, I guess, so much these American guys in the specific project, but I expect we might face similar challenges when we work with our colleagues in Europe as well. But reality compared to the simulation is quite far away. And we have tried to do some of those things in the QCFD setup. Again, I can go fast because these were covered already from the morning. The amplitude encoding, the answers, and the implementation. We have implemented these cost functions, both of them for the non-linear Strager equation. I mentioned it already. It looks like this is some early results without the ancilla. These are all simulations for two different values of the coupling. There has not been any noise or any fluctuations on this. I'm happy to discuss with the team in the morning that they presented similar results, and there seem to be some oscillations there. We couldn't see them at least at the no-ancilla regime. And so what is next? We want to finish up with the understanding really the NLSC and the ancilla regime, including the full simulation. Then would like to go on the start working on optimizing gate decomposition based on what our ion or superconducting guys or whoever we're gonna run this with can do. And that's important to start talking to them as soon as possible. We have some interaction with the AQT guys. And as I said, maybe the Rydberg one could be another possibility. And I'm happy that I had more today. And things that we need to look is how this effective measurement of the cost function of quantum device scales as you implement it, how the fluctuations in the cost functions behave, but like real fluctuations based on the number of qubits you are putting in, the number of fidelities, and the coherence times you have as you grow. Basically, these are small scales so far. We have 4 or 5. But if you try to go more, I expect that the fluctuations will grow, especially on real machines. How we can maybe include measurement of more qubits beyond the ancilla one, the top one, to improve the accuracy in the estimation of the cost function. That's all more or less at the moment. Thanks for the attention, and maybe come down to Crete for the next meeting.
Yeah, thank you very much. The first question is, when is the next meeting? When is the best time?
Say again?
When is the best time for a meeting in Crete? Is it July or August?
Oh, it's too hot, July and August for you Northerners. I would say September, September or May.
All right, so September at least then.
It's also very busy. I wouldn't do July, August. It's all the course of the barbarians coming down. It's too crazy, the tourists. So maybe late September, I think it's a good period, yeah.
For August next year. August next year.
For August next year, yeah.
Or September this year. And August next year. And July. And May. So, Dimitris, you have got the date.
Okay.
All right. Great. Any questions? Yes, Paul.
Yes. Thanks, first of all, for the presentation. And of course, I'm pretty interested in the results of the Lubesch paper you have. Do you try to run it for more than 4 qubits or 2 qubits? I think it was.
I think we not, but Mohammed can come in here. Did the calculation? Mohammed, are you there?
Yeah, I'm here. Yes, so we only have tried with 2 qubits, but we will try to extend it beyond 2 qubits in the next step.
Oh, this would be way more interesting for me. There would be the thing is, we made it for Q as well, for 2 as well, but then for more we screwed up with the noise. So yeah, I'm looking forward to these results, and thanks. It's interesting.
Sure.
Yes, please.
Maybe also regarding to these results, could you maybe explain a bit what's the difference between the ancilla method and the cheat method that you have used?
Well, this is basically the core of the work of Dieter and company. That, I mean, if you don't put this extra, I mean, they can probably do a better job explaining, but let me give it a try. By putting this ancilla, this is an interferometric kind of phase kickback. Most quantum algorithms basically work in this kind of phase kickback up in the upper qubit, and then you measure this and you try to extract some information about this. So if you don't do this, you do the standard variational approach. Let me go back to the. Do I have a picture of the standard variational method? Maybe on the.
I think
chemistry. So so if you just use the. Say again?
You could just go to the other circuit. I think what they're doing is they leave out the ancilla and just measure the qubits directly.
We just measure all the qubits. That's what we do. Yes. We don't do. We just completely delete this part, and we just do a normal variational algorithm here, and then
you need fewer entangled gates, so less noise in the system.
So less noise is expected from your result as compared to ours?
The ancillary result? No, I think you.
The
ancillary method produces more noise.
Okay.
Yes. Okay, because it has got more extra entangled gates in there.
Okay.
Yes.
Because that
You have
only plays a role if you have actually an actual quantum computer, not in the simulation.
Yes, because we switched it on.
Yeah, right. But then, of course, the ancillary method has the advantage that it's scalable, and the other one becomes too
Yes. The problem is if you do standard variation on here, you need to measure all these guys, and you usually measure expectation values of some Pauli operators. That's what we do in chemistry, in standard chemistry, for example. By doing this ancillary method, you basically only measure this guy. And then there's this nice connection shown in the paper that you can extract information about what's happening here, over there. This kind of thinking has been there in quantum algorithms from the beginning. You see how Deutsch's algorithm work, like the most basic algorithm where you're trying to see whether a function is constant or balanced, and you use this kind of control phase kickback up here. You measure the first qubit, and if it's all in zero, you know you have a balance. If it's at least one, it's a constant function. So these things are kind of ancient, but have been evolving through the time. Also through this earlier papers we'll be discussing with overlap, calculating the overlaps and so on.
So basically, adding this qubit does all the integration and adds up all of these kind of exponential terms in one go. But of course, it requires extra gates. And so while you have a small system still, you can just do this individually and do it by hand or task.
Yeah. Yeah.
Did I understand it correct that it was run on the real machine or?
No, this is still simulator, actually. We don't have access either from here. We have access by collaborating groups abroad, but these are all simulating so far.
We haven't tried that. I mean, back then, we had a real device. So,
would it be possible to contact or to maybe
please.
Maybe we should sign up via mail and chat together for
Sure. Yeah, my email is here. Drop me a line. I'll get you in contact with Mohammed and the team that are in the call. My email should be.
I just suggest that you all kind of sign up to the teams, and you can just
we'll do
there.
that.
Because that's why we have introduced this. Actually, in the first
I know.
And you have access to all of the files that are there and all of these things.
True. Okay, but Microsoft really, it's a pain anyway. So we do that.
Yeah,
Meanwhile, drop me a line. It might be more efficient to just do another Zoom call offline, the two groups.
Thank you.
All right. Are there any other questions?
Yes, sorry, Dimitri, can I ask again, because I didn't get it? I mean, you said that you have introduced now some new technique.
No. It's already in the paper of Dieter and Toll, thing in the supplementary. One way to run these circuits is to use this.
No, this I got, sorry, but when you were talking about the quantum chemistry.
In the quantum chemistry, yes, these are different works earlier on. What we did was we found a way to cut down the number of gates, the scaling of the number of gates to calculate correlations. Because in quantum chemistry, basically, you can either do, most people can just do Hartree fork for up to H12, that's what Google has done, or very small molecules with correlations, because this, what they call the UCCSD answer scales very badly. So it's very hard to implement in real hardware. What we did a perturbation theory going above Hartree fork, and not at the full UCCSD, but capturing quite a bit of the correlations. And we implemented that and saw that actually that scales as linear. So in this case, the results basically look like this. So this is where the Hartree fork is. This is no correlations, but that's kind of useless, but that's basically more or less what the state of the art is for anything more than water. And down here, it's called the Moller-Plesser perturbation theory that we took from the normal quantum chemist, and we implemented we optimized the gate decomposition for it. We actually saw how you can do this in a quantum computer. And then down here is what we call the UCCSD of the coupled cluster and the full FCI, which are very hard ansatses. So we managed to implement this orange line using linear depth circuits. That's roughly what we did.
But so linear depth circuit for simulating
simulating
the solution with perturbation theory. Do I understand this correctly? Is this...
Yes. Say again.
Okay. So using perturbation theory to include correlation terms?
Yes, exactly, yes.
And you linearize the circuits that generate...
Exactly, and then we saw that perturbation theory can be actually captured by a linear depth circuit, and it gives you all the interesting correlations that are missing out if you go Hartree-Fock.